This section is on partial fraction decomposition. So the method of partial fractions is used to integrate functions that are rational by splitting up the rational about the denominator. And this is going to be most useful whenever the denominator can factor easily. So just as a background here, when I'm talking about a rational function, a rational is going to be of the form p of x over q of x, where p and q are both polynomials. So for example, you could have, say, 3x plus 5 over 2x squared plus 7. All right, so the numerator is the polynomial that's in the top of the rational. The denominator is the polynomial in the bottom. Now, what I'm talking about here is giving us an ability to split a rational up about the denominator. So just to make sure you fully understand what I'm saying here, if I wanted to split a rational about the numerator, it would be no big deal, because when we combine two rational functions, if they have the same denominator, all you have to do is add their respective numerators together. So the reverse would be true. You could split a single rational function into the sum of two rational functions about the numerator simply by writing two fractions over the same denominator, and you just break up the numerator. But that's not true about the denominator. So we couldn't say, for instance, 3x plus 5 over 2x squared plus 3x plus 5 over 7. That would not be the case. And the reason is how we go about adding fractions together. So if you'll recall from just elementary adding fractions, if you have two fractions that have a common denominator, so let's say 3/7 plus 2/7, then you can just add the numerators and put that over the common denominator. But if you have two fractions that do not have a common denominator, so let's say you have 3/4 plus 5/7, well, you can't add. You have to get a common denominator first. In order to get a common denominator, you have to do some manipulation. So for instance, you could multiply the first fraction by 7 over 7, and then the second fraction by 4 over 4, and you're effectively just multiplying by 1. But you end up with new forms of these fractions where you now have common denominators. And once you have that common denominator, then you can just add together. So if you have a need to split up a fraction about the numerator, it's very easy to do. To split it up about the denominator, it's not, because you have to worry about that common denominator piece. So that's our issue here. What I want to do is I want to take a rational function and be able to split it up about the denominator. So it's going to take a little bit of work here in reverse engineering to really determine how we can go about doing that. So let's see what we have. So one thing that's useful to us is that every polynomial with real coefficients can be factored into linear and irreducible quadratic factors. Okay, so if we take a polynomial that is degree 3, degree 4, degree 5, we can break it down into a product of irreducible linear and quadratic factors. And I'll explain how that's helpful as we go through some examples. Now, another thing is that there is a difference between what's known as a proper rational function and an improper rational function. It's the same terminology as proper fractions versus improper fractions. So a proper fraction, if you'll recall, is something like 7/12. So the numerator is less than the denominator. An improper fraction is something like 7/5, where the numerator is greater than or equal to the denominator. Because the idea is, with an improper fraction, you can rewrite that as the sum of a whole number plus a proper fraction. Okay? Now, what we're going to develop here will only work for proper rational functions. Proper rational functions, what that means is the degree of the numerator is less than the degree of the denominator. And an improper rational, the degree of the numerator, I think I missed a U there, the degree of the numerator is greater than or equal to the degree of the denominator. And the degree being the largest exponent in any of your polynomials, or the number of zeros that exist in the polynomials. This won't really come into play till we see some examples later on, but it's good to mention it now because there is some usefulness to it for now. But if we do have an improper rational function to start with, you can always use polynomial division to rewrite it in terms of what's known as a mixed rational, which is similar to this right here, where you have a polynomial plus a proper rational function. And I'll show you an example of that as we get to it. So let's start with something fairly easy here. Okay, so let's suppose I have this example here. 2 over x minus 5 minus 1 over x minus 2. Now, this is the sum of two different proper rational functions. The degree of the numerator is 0 because it's just a constant. The degree of the denominator is 1 because it's linear. So it's proper. If I want to combine these into a single rational function, then what I would do is, in the same way that I added fractions that had different denominators, I would need to get a common denominator. So I could, for instance, say this is going to be x minus 2 over x minus 2 times 2 over x minus 5 minus, and then take x minus 5 over x minus 5 times 1 over x minus 2. All right, so all I'm doing is just taking the original expressions here and multiplying them by effectively 1. Okay, so each of these fractions here just equals 1, really, because it's the same value divided by itself. But that lets me change the form of the overall fraction. So if I take this product, I would have 2 times the quantity x minus 2, which would be 2x minus 4, and then 1 times x minus 5, so that's subtracting the quantity x minus 5. The denominator would be x minus 2 times x minus 5. And if you'll notice, it would be the same denominator in both of these fractions, so I can actually go ahead and combine that into a single fraction, and that's what I've done here. So I've added into a single fraction, but there is a little bit more reducing I can do in the numerator, and I could make this x, let's see, this will be negative 4 plus 5, so x plus 1 all over. Then this denominator, I'm going to go ahead and multiply out. It's going to be x squared minus 7x plus 10. Okay, so all I've done is just stuff from algebra. I've just taken this fraction or this expression here and rewritten it as this one over here. They are completely equivalent. They have the same zeros in the denominator, and yeah, they're exactly the same, just a different representation. Now the question is, if I had instead given you this and asked you to find that, how would you go about doing it? Well, that's the job of partial fraction decomposition, is to take something of the form that I've given you in the end and rewriting it as the beginning. So we're going to explore how that's going to be possible here. Now, one thing to note is all of these fractions are going to be proper. So for instance, 2 over x minus 5 is a proper rational, and so is 1 over x minus 2. And so is x plus 1 over x squared minus 7x plus 10. And that's always going to be the case. If I start with proper rationals and I add or subtract them, I'm going to end up with a proper rational in the end. You don't necessarily need to see a proof of that, but just kind of go with that as an idea. And it comes from, like, when you multiply the denominators. Here, for instance, I had a linear times a linear, which is going to increase the degree of the denominator to a quadratic. But in the numerator, I had a constant times a linear, which also increased the degree of the denominator, or the degree of the numerator, but not by enough to make it an improper fraction. So it will always stay proper. Okay? So if you start with a proper, you'll end with a proper. It's a good thing to understand. The other thing to note is that the denominators of this original, these are the factors of this denominator over here. And that's actually a really big hint as to how we can go about this. If we can factor this denominator, which we should be able to, then we can take a guess at what the numerator is going to look like and try and solve for what it actually is. And that's really the process here. You just kind of take a guess at what it's going to look like and then try and figure it out from there. It's a little bit more precise in the end, but that's effectively the process. So, for instance, I know that 7x, or x squared minus 7x plus 10, I know would factor into x minus 2 times x minus 5. And I could, go through FOIL to figure that out. Once I figure that out, then those two factors will give me the denominator of the sum of two fractions that could make this original fraction up. So this is just effectively a guess as what the original form might look like. Now, notice I have a constant a. I don't know what it is, but it's some constant a over x minus 5. And then some constant b over x minus 2. Now, how do I know it's a constant and not like a linear function? Well, the reason I know it's not a linear function is because if it were, this fraction would be improper. And if I take the sum of an improper fraction and a proper fraction, I'm going to end up with an improper fraction in the end, but I don't have that. So I know that these are going to be proper fractions. So the degree of the numerator has to be less than the degree of the denominators, which means they should probably just be constants. All right, so that's actually a lot of work there, just coming up with a guess as to what this would look like. Now I know that this should be equal to the end product So how do we go about determining what A and B are to make all of the rest work out? Well, the first thing that we can do is multiply everything in this equation by these denominators and get rid of them. Okay? Now, it's not going to completely get rid of them in every case. So for instance, if I take the product x minus 5 times x minus 2 times a over x minus 5, the x minus 5s would cancel there, but it's going to leave me with a times the remaining factor of x minus 2. Okay? Now, if I do the same thing by multiplying this times b, the factors x minus 2 would cancel, but leave me b times x minus 5. Now if I take x minus 5 times x minus 2 times this last fraction, well, this denominator factors to exactly this. So both of these factors cancel out this entire thing, leaving me with x plus 1. And this right here is an equation that's actually not too bad to solve. It's effectively linear. We just need to determine a method of figuring out what the values of a and b are. And there's a couple of ways of doing that. So the first method that is choosing strategic values of x. Okay? And what I mean there is, so if I let x equal 2, then I would end up with a times 2 minus 2 plus b times 2 minus 5 equals 2 plus 1, which can simplify some. And 2 minus 2 would be 0, and anything times 0 is just 0, so this whole term goes to 0. 2 minus 5 is negative 3, so this would be negative 3 times b. 2 plus 1 is 3, and if I divide by negative 3, it reveals that b has to be negative 1. So for this to be true, b would have to be negative 1. So we still don't know what a is, but we've just learned that b is negative 1. Now another value of x that I could choose that would be strategic would be x equals 5. When I plug that in, it would make another term with a variable cancel out, which would allow me to solve for another one, the other variable, that is. So if I plug in x equals 5, I would have a times 5 minus 2 plus b times 5 minus 5 equals 5 plus 1. So 5 minus 5 is 0. Anything times 0 is 0. So 5 minus 2 is 3, so this would be 3a equals 6. And when I divide by 3, I get a equals 2. So the a term, the value above the x minus 5, is 2. And if you compare that to the original, 2 over x minus 5, and instead of writing plus negative 1 over this, it's just minus that, but that's the same thing. So effectively, we've come up with a means of decomposing the n term and getting back to the sum of two fractions. Now, I said that there's different methods of solving this equation, so let me show you another. Although the choosing of strategic values of x is always the easiest, and you should always use that when you can. Now, it's not going to be entirely possible in every situation, but when you can't, another method is using either just picking other values of x, and that gives you an equation that you can work with, I'll show you an example with that, but one here that could also work would be the method of equated coefficients. Okay, the method of equated coefficients tells you to just take the original equation and work with it directly. So if I distribute A into this set of parentheses, I would have A times X minus 2A plus B times X minus 5B equals X plus 1. And then everything with an X I group together. So AX plus BX. And everything that's a constant I group together. So negative 2A minus 5B equals X plus 1. And I factor out common factors. So X times A plus B. And the negatives here I'm just going to leave in. It's usually the common factors that are variables that you would pull out. 2A minus 5B equals X plus 1. Now the idea is if you're trying to get this polynomial over here equal to this polynomial, then the only way that's going to happen is if the coefficient on the x term is equal to the coefficient on this x term. So what we would need is A plus B to be equal to 1, because the coefficient here is just 1. And we would also then need this constant to equal this constant term. Because it's the only way these polynomials are going to actually be equal. Now that gives me a set of equations that can be solved simultaneously. And you do need to generally do this with equated coefficients. So effectively just pick something that you can multiply the top or bottom equation by, so that when you add it to the other equation, so 2a plus 2b equals 2, and then I have negative 2a minus 5b equals 1. We'll add these equations together. This becomes negative 3b equals 3, so that we find that b is equal to negative 1. And then if a plus what I just learned to be b is equal to 1, then that means a minus 1 is 1, or a equals 2. And I've solved for both coefficients and got the same results using equated coefficients rather than picking strategic values of x. Which is why I say that picking strategic values of x is the best way. You should always do that. It's the easiest thing. But it won't work in every situation. So when that method doesn't work, then you can rely on something more like equated coefficients from there. Now, the last step in the process would be to actually do some integration, because you have to admit we haven't done that yet. But before we get there, let me just state formally a process for decomposing rational functions with distinct linear factors. All right, so let p of x over q of x be a rational function where p and q are both polynomial equations and q of x degree is higher than the degree of p of x, so it's proper. Then if q of x can be written as distinct linear factors, so every linear factor is different from all the other linear factors, and there are no irreducible quadratic factors, then p of x over q of x, so this rational, can be written as the sum of all of these terms. So just take each linear factor from q of x, put a constant over that, add those together, and that's going to be your structure of the decomposed fraction. So essentially gives you a method of finding the guess. And then integrating in the end, once you actually have this split up, is fairly straightforward just using logarithmic integrals. So for instance, the process here, we would first factor the denominator if it wasn't already. And you just have to do the denominator. You don't have to do the numerator. So here, there's a common factor of x. Let's factor that out. And when that's done, I can factor the remaining quadratic here into, let's see, 1 and 2. If that's positive and that's negative, that would be great. Now, the next thing is to give the form of the decomposed fraction. So we would have the original function 5x squared minus 4x minus 4 all over x cubed plus x squared minus 2x equal to, we take each of these linear factors and split them up with just a constant in the numerator. So each of these constants can be different, so I need to make sure I have a different constant for each one, and go from there. All right, then the next thing is to solve for those coefficients. So generally what I would go ahead and do is multiply everything through by these factors. And here's what's going to happen. So these factors are equal to this denominator. So you end up with 5x squared minus 4x minus 4. So just that polynomial in the numerator. For this fraction here, you have a over x. So the x would cancel, so that leaves you a times the remaining factors. Oops. And then you have b, the x minus 1 would cancel, so b times the remaining factors from there. And this is getting long, but you'll be surprised how quickly the rest of this goes after you write this all out. So let's see, c times x minus 1. All right, now we pick strategic values of x. So let's say we choose x equals 0. Now, if I pick x equals 0, then I would have, this would be 0, negative 4 times 0 would be 0, so I would end up with a negative 4 on the left-hand side. And then a times 0 minus 1 is negative 1. 0 plus 2 is 2. The b term would go to 0, and the c term would go to 0. So I really have negative 4 equals negative 2a, so that a is 2. Okay? Now, if I let, say, x equal positive 1, so that would cancel out another variable. So it's just the zeros of this reducing here. All right, so plugging in positive 1, so this would be 5 times 1 squared, so that's just 5. 5 minus 4 would be 1, and then 1 minus another 4 would be negative 3. So we get negative 3. And then when I plug in 1 here, this term goes to 0. Now I'm left with b times 1 times, let me be careful there, 1 times 3. And then the c term would go to 0. So I'm left with b equals negative 1. And lastly, if I let, let's see, x equal negative 2, this term's going to get a little trickier, but let's just work it through as best we can. 5 times negative 2 squared, that's going to be 5 times 4, which is 20. Then that would be plus 8 and minus 4, so that will all become 24. And let's see, this term will go to 0, that term goes to 0, and then I have c times negative 2 times negative 3, so 6c, so c equals 24 over 6, which is 4. Okay, now that means that this integral is now equal to a over x, and a is 2, so 2 over x plus b over x minus 1 plus c over x plus 2 dx. Now, here's the nice thing. The rule for integrating logarithms is that if you have something of the form 1 over u du, then that just becomes the natural log of the absolute value of u plus a constant. So that's effectively what I have in each one of these terms. U is a bit more complicated in each of these two terms, but if you used u substitution, du would just be x. It would just be 1, so it's not going to mess it. It's not going to make anything more complicated. So this will become 2 times the natural log of absolute x minus the natural log of absolute x minus 1 and plus 4 times the natural log of x plus 2. And then we're done. That's it. One thing I want to mention is these absolute value bars. I'm putting these inside the parentheses because when you type those into your homework system, you'll need to do it that way because it doesn't see the absolute value as a grouping symbol. It sees it as a function. So you need to make sure you type it in that way. But that's the only funny thing about it. So once you get the partial fractions done, the integration is actually pretty straightforward for these distinct linear factor ones. All right, now I know this video has been going fairly long, but I do have one more example I'd like to do for you, just so you see it, and then I'll let you do some homework. Okay, here's another example with some distinct linear factors, which you may see or you may not see right away. First step you'll always do, of course, is to just factor the rational function. And in this case, we have 3x plus 1, and this denominator of x squared minus 4 being the difference of squares, we would have x plus 2 times x minus 2 in the denominator. So that's two linear factors that are distinct. So that means there will be some constant above the x plus 2 and possibly some other constant above the x minus 2. To figure out what those are, we just take this statement and multiply everything through by the denominator. So when I multiply by x squared minus 4, that leaves me just 3x plus 1 on the left-hand side equals a times x minus 2 plus b times x plus 2. Now, choosing strategic values of x in order to solve this, if I let x be 2, that would be 3 times 2 is 6 plus 1, so that's 7. And when x is 2, this term with a cancels out because 2 minus 2 is 0. Then I have b times 2 plus 2, which is 4. So b equals 7/4. And the other strategic value I could pick, of course, is negative 2. 3 times negative 2 is negative 6 plus 1, so that's going to be negative 5, equals a times negative 2 minus 2, which would be negative 4. So that a is equal to 5/4. All right, so that means I can rewrite this original statement as the integral with 5/4 over x plus 2 plus 7/4 over x minus 2 dx. And then both of those will integrate pretty easily because the numerator is almost the derivative of the denominator in each one. It's just off by a multiplier. The derivative of the denominator is just 1, so we really can just take these constants out of the numerator and write 5/4 times the natural log of absolute x plus 2 plus 7/4 times the natural log of absolute x minus 2. And that'll do it.